So remember last time we did systems of ODEs, and we found that since we'd proved Picard's theorem for this one ODE, we basically just had to essentially do this and then prove it for systems. Then you could just prove it. You have to be a bit careful as to how you define the Lipschitz condition in terms of having to now use the L1 norm, but everything worked through, okay? But one important thing to point out is, remember that in the one when we had just one ODE, we used comparison principle where we said, okay, if U is greater than F, U dashed is greater than F, and V dashed is less than F, what can you say about U and V? Notice that we can't just do this and carry that over to systems, because what does it mean one vector is bigger than another vector? That doesn't mean anything. You'd have to use norms. But then if you use norms, positive and negative will have the same norm if you take a modulus. But negative would decrease this, positive would increase it. So the comparison principles do not carry over. So we'll not go into that, but that's an important point to mention. So now we've done systems, and then the last thing we're going to do on Picard is higher order ODEs. So suppose we've got second order, y double dashed equals f x y of x, y dashed of x. Then we're going to have y of a equals b, y dashed of a equals c. Then all we do is we set y1 of x to be y, and y2 of x to be y dashed of x. And then what does that give us? Then that'll give us that y1, y2 dashed is equal to, well, y1 dashed will just be y2, because y2 is y dashed and y is y1, and then y2 dashed is y double dashed, which is the f. So we can just write it like that, and so that becomes our system. So here, abusing notation, sorry about that. Where the f of xy is just y2 and f. Okay, and then the initial condition is just y of a is equal to b, where b is bc. Okay, and so now if f, oops, forgot to put that in. So if f satisfies Lipschitz condition, with constant, say L2, then the vector f will satisfy Lipschitz condition with constant L2 plus 1. Why is that? Well, if we look at the norm of f x1, y1, y2 minus y some other thing, that's going to equal, remember you take the modulus of each component. So that'll be y2 minus y2, because that's the first one. And then the second one will be big F x y1 y2 minus big F y1 y2 that. And leave that as is. Then since this is Lipschitz, that's going to be L2 times y1 minus y1 hat plus y2 minus y2 hat. And then you can see that's going to be less than or equal to L2 plus 1 times the thing, times that. Okay, simply because this thing here we can just is less than or equal to that. Okay, so the key thing is it satisfies the Lipschitz condition, and then we can go through and do everything that needs to be done. Okay. So the obviously for nth order, n bigger than 2, just do the same thing. y1 is y, y2 is y dashed, y3 is y double dashed, etc., etc. yn minus 1 is, well, sorry, you'd have to go to yn plus 1 is yn, etc. And it all works out, okay? I should write that down. You just set y1 equals y, y2 equals y dashed, and then write down to yn of x equals yn minus 1 dashed, okay? So then you'd have system of n ODEs, first order ODEs. Right, so we've spent a good 2 weeks on looking at existence and uniqueness. So now we're going to move in to what do these solutions actually look like, okay? And we're going to do that by looking at systems of equations. So we're going to talk now about plane autonomous, if I can spell it correctly, systems of ODEs. And we're going to look at coupled, so 2 ODEs. That's why it's called plane. So we'll write down dx by dt. Okay, now strictly speaking there should be a t there, but I'm not going to do that. Strictly speaking this should be x of t, y of t. So I'm being a bit sloppy. So this is called a plane because the solution is x and y, and we will draw a plane to put down the solution, so that's why it's plane. So that's because it's 2 equations. And what does autonomous mean? It means that x does not have explicit, x and y do not have explicit dependence on t. Okay, so of course they implicitly depend on t because little x and little y depend on t, but there's no explicit dependence. So for example, x could be x squared plus y squared, but it can't be x squared plus y squared plus t. Okay? And then we have initial condition. And now what we're going to do is we're going to assume Picard. So we're going to assume Lipschitz, etc., a continuity, boundedness, etc., so that there's a unique solution. So there's a unique solution. Okay? So now we're not going to worry about norms and stuff like that. We're going to say, let's assume that everything is well behaved, so we've got a unique solution. Now the question is, what does that solution look like? Okay? And what the solution will do is it defines a trajectory or what's called a phase path in the phase plane. So what you've been used to doing, if you have like one ODE, say dx by dt equals big X, then you plot x as a function of t. Okay, you got one independent variable and one dependent variable. Now here we've got two dependent variables and one independent variable. And what we do is we plot the two dependent variables. So what we do is this. And then with this setup, initial condition A, B, and then we know a solution exists, and we know it's unique, and so we just plot that solution. So solution, like that. Maybe it goes around, maybe it goes and goes somewhere else, like this. Okay? And then that's called this is the phase plane. And this is the phase trajectory. Okay? And obviously if you're drawing a phase plane, you don't put phase trajectory slap bang in the middle of the phase. You would just have, that's just me to show that that is there. Okay? So first, one thing to point out. If we've got a solution as a solution of 2.1, then for every fixed number t0 real number, then x of t defined as shifted along x of t plus t naught, x of t plus t naught. Solve 2.1 and they trace the same path. The same path. Okay, so what does that mean? What that means is that here we had this solution here. So if we were now to define another function, which is, so for example, this is x of naught, y of naught, and then suppose we took t naught to be 1. So then if we defined this new xy thing to be x of 1, y of 1, which would be here, and then we ask the question, how does x hat, y hat change over time? The answer is, it goes like this. So it's basically the same solution, just shifted. And why is that the case? Okay, so what we're saying is that x hat and y hat satisfy 2.1. So how do we get that? Well, dx hat by dt is going to equal x of, sorry, before you, it's going to be going to equal that, and that's going to equal x t plus t naught, y t plus t naught. Okay, because that is just that, and that satisfies equation 2.1, so it's this, and now that is x hat of t comma y hat of t. Okay? Now, crucially, the reason why this works is because this doesn't explicitly depend on t. Because if this had an explicit dependence of a t here, then we couldn't go from here to here. Okay? And so similarly for that one. And so that means, and then also we would have that x hat of t naught would equal x of naught, y hat of t naught equals y of naught, and therefore by Picard, therefore solution exists and is unique. And so solution to this exists and it's unique, but it satisfies the same equation as x and y did, so it must be the same path. Okay? And then the second proof, second thing to point out is that through every point x0, y0, there exists a unique trajectory. Okay, so what does that mean? That means, so here's one trajectory. And then if I now plot another trajectory, so that was a certain initial condition here, I get this solution. If I take another initial condition here, I get another solution. Could that solution go like this? And the answer is, from NB2, no. Because if I take this to be x0, y0, then there's only one trajectory through that. So what that means is that, i.e., trajectories can't intersect. And why is that then? Well, if I started off here with this, now let's make this my initial condition. Then Picard says there's a unique solution. So there can only be one trajectory coming out from here, not two. So they can't meet. Okay? But one thing that could happen, but they could asymptote to the same point. As t goes to infinity or t goes to minus infinity. So what that means is that they could get closer and closer to each other as t goes to infinity and get arbitrarily close to each other but not touch each other. That would satisfy Picard's theorem, or doesn't contradict Picard's theorem. Okay? And so the proof of this just follows from Picard. Okay? And simply because we start off first of all, we have to first of all show that there is a trajectory. Well, if we start off with this as initial condition, then Picard implies there's a solution. So there is a trajectory. Is it unique? If not unique, then there exists another solution that must pass through it. Okay? So there must be some other solution that at some t0 passes through the point. Now set u of t to be equivalent to x of t minus t0, v of t to be equivalent to, sorry, that should be just x. That should be x hat t minus t0. Then we know from this first part up there, if we just replace t0 by minus t0, we know that this is a solution. So this is the solution from the first part, from NB1, and u of naught is going to be, sorry, I've got this the wrong way around. That should be pluses and pluses. So u of naught is x naught, because u of naught is x hat of t naught, which is x naught. V of naught is y naught. So this satisfies the differential equation from NB1. It has the initial condition as this one, so it must be the same. Implies that then u v is the same as x y, and therefore this seemingly new solution we got is just a time shift of xy. Okay? So what we will now do is go on to talk about critical points and closed trajectories. So if I just go slightly off what's in the notes, and we'll come back to this later on, if I've got that, so suppose I plot the curve x equals 0, then above this curve x will either be positive, big X will either be positive or negative, and then if it's positive, then below the curve it has to be negative. Okay? Why is that? Well, if it's positive here and it's negative here, then by the intermediate value theorem, it would have to be 0 somewhere here. And it's not, it's only 0 here. So I can immediately say above here, let's assume that x is bigger than 0 up here. Then I can immediately say, oh, little x is going to be increasing here, little y is going to be decreasing here. And then suppose for y, suppose that's y equals 0. And suppose y is bigger than 0 here, less than 0 here. Then what I've done is I've split the domain up into 4 regions, and in each region I know what little x is doing and what little y is doing. I know the directions of the components of those vectors, so I can then plot the direction of the trajectories. So all I need to do then is just join those directions up, and that'll be my phase trajectory. And now the question is, how do I do that? And the first thing we do is we look at points like this. This point here where big X and big Y intersected with each other. And that's called a critical point. So critical point x naught, y naught is such that x of x naught y naught is equal to y of x naught y naught is equal to 0. And sometimes that's called a steady state, because if we're writing where we've done here in terms of time, then if at some point these are both equal to 0, it means at that point x and y aren't changing in time, so they're steady. Sometimes it's called a stationary state. And sometimes it's called an equilibrium point. And obviously in this diagram here, it's unique, but there's no reason why it should be unique. Okay? Imagine a situation, in fact, it could be an infinite number of solutions if big Y was equal to big X. Okay? So if we have a closed trajectory in the phase plane, so in other words, if we have a trajectory, say, that goes like that, that's called a periodic solution. We call that a periodic solution. Why is that? Okay, so suppose we start off here and we give out our trajectory, and it goes like this, and it comes like this, and it comes back to here. What will it do? If it's periodic, that means it has to keep going around, because if you think of x, what is x doing? X is going like this, because to get the x you project down here, so x is going like that, and if it's periodic, when it comes back, it should go forward and back, forward and back. Y should be going up and down, up and down, up and down. So when I get to here, I need to keep going around here. And so the question is, what would happen if, when I came back, I didn't continue going? Suppose I came back to here and then shot off here. Is that possible? Don't draw this because it's wrong. Well, now the answer is going to be no. Take that as our initial condition. If this happens, then I've violated the uniqueness condition. So when I get to here, I have absolutely no choice. I have to keep going around. Okay? And the proof of that is, suppose x of t naught, y of t naught, so where t naught is finite, and actually suppose that we get to the stage where this doesn't hold for some t naught finite. So then set x of t to be x of t plus t naught, y of t to be y of t plus t naught. Then we know that x hat and y hat is a solution. So x hat, y hat is a solution because of what we've done before. And x hat of 0 is x of 0, y hat of 0 sorry, I've got this the wrong way around. Sorry, we should have that's equal to that. Sorry. Therefore, x hat, y hat is solution, and x of t plus t naught, which is equivalent to x of t. Right, so what have I done there? Said that x of t plus t naught is y hat. Y of t plus t naught is y hat. That's the definition. But x hat and y hat satisfy the same initial condition as x and y, and they satisfy the same ODE. So this must be equivalent to that. That must be equivalent to that. So that means that if I go around and come back to here, then what must I do next? I must continue, okay? Because x at t naught, when here I will have got to here, and then as t goes past t naught, what's x of t plus t naught? Well, it's x of t. So it's that one there, and then I keep going round, okay? So let's take a simple example, one that you may be familiar with, which is the harmonic oscillator. So this is x double dot equals minus omega squared x, where omega is real. So you should have come across this before. Simple harmonic motion. So if we set this as x dot equals y, then what's y dot? Well, y dot is x double dot, which is minus omega squared x. So that's big X, and this is big Y. And this has critical point at xy equals 0, 0. And note that if we were to take omega squared x squared plus y squared, the d by dt of that, that's going to be 2 omega squared x dot plus 2 y dot. And so what does that give us? Well, forget about the 2. If I multiply this by omega squared x, gets me that. And multiply this by y, gets me that. Add them together, I'll get 0. Put it another way, that's omega squared xy minus omega squared xy, which is 0. And then you should remember that's the energy. So that implies omega squared x squared plus y squared is constant, which implies an ellipse in the phase plane. Okay? So it would be something like that. And of course, you could just solve that straight away. It's cos omega t plus sine omega t. Okay. So now you might be asking the question, why am I sort of obsessed with trying to draw this phase plane? Why don't I write x as a function of t and y as a function of t and plot that? Well, this is a sort of trivial example, but imagine if this was, say, two species interacting with each other. Say a predator and a prey were interacting with each other. Then what we might want to be looking at is how do their densities relate to each other? So what we might be interested in is, as one of these is going up, is the other one going down? That would mean it's a predator-prey. Or could it be, as one is going down, the other one is going down as well? So that would be competition. Or it could be, this is going up and this is going up, which means they're both working together. That's called mutualism. And so, of course, you could get that by plotting x as a function of t and y as a function of t. But the easier way to get it is to be able to look at a diagram like this. And then you would be able to see, oh, as y is increasing here, well, if it was predator-prey, there wouldn't be negative values. But you look at here, you could sort of say, oh, look, as x is increasing, y is decreasing. So you can bring things like that out of here. Also, it's easier to draw the phase plane than to solve these equations analytically. I mean, obviously, we have a trivial example there which you could solve, but in general, this will be a horrible nonlinear function. This will be a horrible nonlinear function, and you won't be able to solve it. Okay? So what we do then is we first of all look at the critical points. The points where these are equal to 0. And then what we'll do is we'll linearize the system about the critical point, and that'll get us a linear set of ODEs, which are easy to solve. So what that'll mean is that if we have, say this is x equals 0, and this one is y equals 0. So we've got two critical points. So our linear analysis will be able to tell us what's the behavior near here. Because these are the points where the trajectories cross. These are not trajectories, but what this means is that you could have more than one trajectory going through here. And then up here, we know big Y is bigger than 0, big X is bigger than 0, etc. So we can have a sense of what must the directions look, and the combination of those two means we can draw the phase plane without ever having to solve the equations. So how do we go about doing that? Well, we now talk about stability and linearization. So definition, a critical point AB is stable if given epsilon bigger than naught, there exists a delta bigger than naught and a T0 such that for any solution x of t, y of t of 2.1, for which square root of x plus y of t naught minus b squared is less than delta, the square root of x of t minus a squared plus y of t minus b squared is less than epsilon for all t bigger than t naught. And what that means is that if I start off at this point here, and say this, and this is my point A, B, and for example, start off with having, if that stable point, essentially what that means is that if I perturb a little bit away from there, I'll always stay close to it. Okay? So any trajectory when I move a little bit away from here, it's not going to shoot off anywhere. It's going to stay in the neighborhood of there. Okay? And so what that is saying is that if I look at the solution that's very close to here, then I can trace back a trajectory that'll be really close to this. That's what that's saying. And we've used the Euclidean norm. Other norms are available. But we're using Euclidean norm. Okay? So what we will do the next time is we will take the critical point, we will linearize about it. That'll give us a linear set of coupled system of ODEs, and hopefully you know how to solve those. You look for solutions e to the lambda t. Lambda ends up being, you have to get a determinant as 0, and then lambda ends up becoming an eigenfunction. eigenvalue of a second or a 2 by 2 matrix, and then we'll go through all the different possibilities. Are the eigenvalues positive? Are they negative? Are they imaginary? Are they equal to each other? And what different behaviours does that give in the locality of the critical point? And once we've done that, then using that together with drawing these lines where big X equals 0 and big Y equals 0, those are called null lines, we can then draw the whole phase plane, the whole phase trajectory. Okay?